Okay. H block, say hello to D block. Okay. Tell them that, all right. So, we're going to be filming today. Do I look okay on that?
Your head's kind of cut off.
My head's cut off?
That's fine, yeah.
You
It's
can
not
see
fine. Yeah, it's fine. It's good now.
No, is it all right? I mean, is it,
Yeah, it's
do I
good.
need to move it back an inch?
No, you're good.
It's good, it's good.
All right. You know that this is not going to work, right? But we're going to give it a try. We're going to pretend it's like it's like a regular class. Yes? I'm a little nervous. All right, let's get out your homework. Get out your homework. Let's go through some of these problems for conversion factors. Now, conversion factors. You're not going to be great at conversion factors. You're not going to be great at solving problems. We're going to be doing this all year long. You're going to get better at it. So don't get frustrated with it, okay? Just keep moving. The key is write down what you first learned, what's given, what's the unit you want to go to, and then finally, what are the conversion factors you want to use. Cross them off as you go along, and you'll be all set. So here we go. The first problem was number 69.
Yeah.
Okay. Perform each conversion, kilograms to grams, milligrams, meters. Are we good with that?
Yes.
Okay. What did King Henry drink? Chocolate milk. Before what? Before he died. You got to know those, right? You got to know how to go from one to another. I assume you know how to go from one to another. So I'm not going to go over that problem. The next problem is 83. A runner wants to run 10K. Any of you guys runners? Anybody runner? A little bit? You ever run a 10K? That's sort of
5Ks, Thanksgiving, turkey shot.
5K. And I think cross country is usually 5K, right?
Yeah.
But the classic race, road race, is a 10K, 10 kilometer. Here we go. A runner runs 10 kilometers. She knows that her running pace is 7.5 miles per hour. How many minutes must she run? Many minutes is it going to take her? Okay. So, I always write down what's given to me. Then I can put away the book. Can they see that?
Yeah.
Okay. Jason, can you see that? Okay. So I always write down, okay, so here's what we have. Kilometers, and I want to end up in minutes. So I'm going to end up in time. So that tells me I'm going to have to flip this. Okay, that tells me I'm going to have to flip this at some point. So I'm going to see how many, 10 kilometers is how many miles? Yes? We'll do that first? Yeah. Oh, you can tell? All right, so I got 10 kilometers. I want to change that to miles. And what is the conversion factor? 0.62 miles? 0.62 miles for 1 kilometer. There's another one. Yeah.
1.609 kilometers.
Okay, but in any case, this is going to get me 2 miles. Yes? That'll tell me how many miles. Yes?
Yes.
Okay, so how many miles is that? 6.2 miles. Now, they run 7.5 miles per hour, so I can divide that by 7.5, and that will give me how many hours? Yes? How many hours is that? How many?
1.2.
0.8. Remember, it's smaller. 6.2 miles she's running.
I just said backwards.
Yeah, you must have. And it's 7.5, so that gives me 0.8. Now, here's another thing, 0.8 hours. Here's another thing. Always make sure that your answer seems logical. That's really important. So 6.2 miles is less than 7.5, so it has to be less. So then we have 6.8 hours, and we can change that to minutes, yes? And you know how to do that. I'll put hours on the bottom, 1 hour, 60 minutes, and there's your answer. We good? Okay, next problem was what? Number what?
Number
105.
105. Ethylene glycol has a density of 1.11 grams per centimeter cubed. Always write down what is given. 1.11 gram per centimeter cubed. I'll write it this way, centimeter cubed. What is the mass in grams of, so I want to find the mass in grams, there's my G, of 387 milliliters. Okay, now, what is the one conversion factor that I want you to remember? Really important, yeah.
centimeters cubed to milliliters.
Right, 1 centimeter cubed equals 1 milliliter. 1 centimeter cubed equals 1 milliliter. So that makes it pretty, that's going to make it pretty easy right now. Okay? So now I have 1.11 gram. Can they see?
Yeah.
Good. 1.11 gram per centimeter cubed. Let's change that centimeter cubed to, oh, wait a second, milliliter. That's milliliters, right? Well, I know that 1 milliliter equals 1 centimeter cubed. So now I got 1.11 gram per centimeter cubed. I'm doing something wrong here, aren't I? Now I could just multiply that times 300. I should really start with 387, shouldn't I?
Why are you putting the centimeters cubed on the bottom?
Because I'm going to use this eventually.
Okay.
So I should have started with 387 milliliters and then changed that to centimeters. So let me just do that. So I got 387 milliliters. I want to get it to centimeters. 1 milliliter, 370 milliliters.
I think we're trying to find it.
Oh, they're trying. Oh,
Yeah.
We're giving it in centimeters.
they're giving it. Is this milliliters? Did I get this?
We were given the mass.
You were given
Oh,
the
sorry.
mass of.
We were given the volume in milliliters. So we're trying to find the mass. In
You're trying to find the mass. All right.
the
So.
second one's volume.
My bad. So you got 387 milliliters. That's what you're given, yes?
Yeah.
Yeah.
Okay. So I got to change that to centimeters. So it's 1 to 1. So it's 1 centimeter cubed equals 1 milliliter cubed. 1 milliliter. So that gives me 387 centimeters cubed. And then I could just multiply that times my density. Yeah, why did I make this so hard? 1.11 gram over 1 centimeter cubed.
So that times 387.
And that just gives me my answer. I think I made it harder than I should have made it. My bad. 119. A car has a mileage rating of 38 miles per gallon. Can I erase this? Everything that's been done here?
Yeah.
38. What does it say? 38 miles per gallon? 38 miles per gallon. How many miles can a car travel on 76.5 liters? So I have 76.5 liters, and I want to find out how many miles it can travel.
They can't really see that up there.
Pardon me?
They can't see that up
They can't see that high?
there.
Do anything
a
below
little
your
lower.
head.
Oh, cool. All right, thank you. 76 point, can I see that?
Yeah.
Yeah.
76 point what?
5.
76.5.
6.5 liters is how much we have?
Yep.
Okay, and we want to find out how far we can travel?
Yeah.
So now you just got, we know what we have, Always write it down. Here's my conversion. How far to travel? So, it's 30, I gotta change, what do I gotta change?
Gallons to liters.
Gallons to liters. Well, I gotta change the liters to gallons, yes? You gotta change the liters to gallons. So I got 6.5 liters. What is my conversion?
3.75.
What is it?
3.75 liters per gallon.
3.75 liters per gallon, right?
I think it's 78.78.
78.5, yeah. 3.785.
3.785 liters per 1 gallon. Now, if you get different ones, that's okay. We'll talk about significant figures in a minute. This is going to give me the number of gallons. And then with that answer, what do I want to do? I want to divide it by 38, yes? So now what I've got here is gallons, and I want miles, so I'm going to put down 1 gallon is 38 miles. So my answer will be in miles. And that's what we want. Okay. And we'll have some time, like I said, we're going to keep working on this, keep working on this, keep working on this. But I want to mention a couple of things first. And the first one I want to talk about are 2 terms. Okay? And I'm not going to test you on these terms right now, but you need to know them because we're going to use them. And lots of times we use them interchangeable. Interchangeable. Now remember, anything starting right this minute will not be on your assessment next week, okay? And the 2 terms I want to talk about are accuracy and precision. Accuracy and precision. And we tend to use these terms interchangeably, but they are a little bit different, okay? Accuracy is how close we are to the given answer or how close we are to the given, what we should be, okay? So how close we are to the correct or the given, whatever you want to call. Yes?
Yes.
The correct, the given, whatever that is. Precision is when you have multiple readings. How close are those readings together? So how close are the readings that we're getting together? Accuracy and precision. So let's just do a little,
What do you mean by readings?
pardon me? In other words, your
Measurements.
measurements. Measurements is a better term, you can put that in here. So I've got here a dartboard. Anybody throw darts? It's a pretty bad looking dartboard. Anybody throw darts in the class? You throw darts? You throw darts? All right, Brady, get up. Stand up. Stand up. You guys can't see this. Stay back there. I'm going to throw you 3 darts. All right? You ready? Put your hand out. Here's 1. Here's 2. Here's 3. Thank you. All right. Wait. Throw the first. Hold on a second. Throw the first dart. Throw the second dart. Throw the third dart.
Hold on.
Wow.
Okay. Now, are they accurate?
Yes.
No.
No. Are they precise?
Yes.
They are precise. Okay. So, you get the idea, right? If we throw 3 and they end up there, they're accurate and precise.
When
Yeah.
is it accurate but not precise?
Well, I get 1 here, 1 here, and 1 here. So 1 would be, the middle one would be accurate. The others would not be precise. You know, you're shooting foul shots, okay? And you shoot 10 foul shots and they all hit off the front rim and bounce down. You're not accurate, but you're precise because they're all hitting the same area. All right? Accuracy and precision. That's really important. That's really important because when we talk about measurements, the precision is going to be on what kind of instrument did we use. So in other words, if I am weighing something and I've got a scale, can they see over here?
Yes.
Don't come here. They got a scale, a balance. Does that look like a balance? No, not at all. I put something on the balance, and the balance gives me a reading like this, 3.114, okay? And then I got another balance, and the reading on this balance says 3.1, okay? So one says 3.114, the other says 3.1. Now, this one, 3.114, is much more precise. Because if I take a bunch of readings with that, I'm going to get to the hundredths or thousandths place. Okay? Whereas the bottom one is not as precise. Because it's only giving me to the 10th. If this is grams of grams. Does that make sense? And that's why it's important. Now, we're going to be talking about, and you're going to be doing some reading and stuff like that, we're going to be talking about the math of chemistry, to understand chemistry. And when we're talking about chemistry, we're dealing with atoms. And what can you tell me about atoms? They are incredibly what? Small. Atoms are incredibly small. So when we're talking about the size of an atom, the number is going to be incredibly small. When we're talking about the number of atoms, the number is going to be incredibly large. So, the simple way for us to do that is to use something called scientific notation. And you guys all familiar with scientific notation?
Yeah. Little.
A little bit? All right, what about you guys on tape? You guys that are watching this at home right now, on Tuesday, fully dressed, not wearing pajamas, and wide awake, with your phone turned off. Of course, thank you. Scientific notation. Let's figure out how it works. Because, like I said, we don't want to be writing all these zeros our whole life. Basically, scientific notation is a way of writing things to the power of 10. 3, 1, 4, 6, 7, 8. Okay? Or 0, 0, 0, 0, 0. It's a lot of zeros. When I write something in scientific notation, I write one digit and a decimal point. Okay? And then after the decimal point, as many digits as you need to write depending on significant figures, which we'll talk about later. Scientific notation. Is always going to be one digit. Decimal point. So, in this case, it would be 3.14678 times 10 to what power? Well, we're just going to count. So we're going to start here. We're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times 10 to the 10th. So each place you move over, it's to another power of 10. If I have 0.0014 and I want to put that in scientific notation, that's going to be equal to 1, 2, 3, 1.4 times 10 to the what? negative 1, 2, 3. So if you're going to the right, it's the negative. If you're going to the left, it's the positive. Yes?
In the book, for like checking the answers, sometimes it had it in scientific notation, and sometimes it had it like just as the longer number. How do you know
When to use it? Okay. If I don't tell you specifically when to use it, it's up to you. All right? If I don't tell you specifically, it's up to you. Now, if you multiply numbers with scientific notation, 4.5 times 10 to the 5th, and I multiply that times 2.1 times 10 to the 3rd. What do I do with my exponents? I add them. I add them. Now, everybody get out your calculator. You'll start doing this stuff. You're going to start doing this stuff. You add them.
And then we multiply digits.
And then you multiply digits. So you go, there are two ways of doing this on your calculator. You can put the whole thing in. You can put the whole thing in. You can put the number in 4.5 times 10 to the 5th times 2.1 times 10 to the 3rd, but you need to put it in parentheses. Okay? So you can do it that way, or you can multiply 4.5 by 2.1 and then just add the exponents. So can you guys all try that? Everybody try that number.
It's the same thing when it's negative, right?
Same thing with its negative. Everybody got that number? Everybody's got it. What'd you get?
9.45
Times 10 to the 8th?
Yep.
9.45 times 10 to the 8th. Okay, now try this. 4.5 times 10 to the 5th times 2.1 times 10 to the minus 3rd. Do it on your calculator. You know what it should come out to, but make sure it comes out that way on your calculator. Everybody do it. I don't see everybody doing it. Everybody has to do it. You need to make sure that you don't screw up with your calculator. It should be 9.45 times 10 to the 2.
Yes.
Is that what you got?
9.5.
9.45 times 10 to the 2nd. Now, when you're dividing with scientific notation, 4.5 times 10 to the 5th divided by 2.1 times 10 to the 3rd. You either put it in your calculator or you're just subtracting the bottom from the top, the denominator from the numerator. So, if I make this, I'm going to make this 4.2. Because I know 4.2 divided by 2.1 is 2, right? So I know this should be 2 times 10 to the 2nd. Do it on your calculator. See if you get that. Because when you divide using scientific notations, you subtract. Everybody got it? Okay, try this now. 4.2 times 10 to the 5th divided by 2.1 times 10 to the minus 3. And what do you get? Try it on your calculator. Got it? It should be 2 times 10 to the 8th. Is that what you got?
200 million.
Pardon me?
200 million.
Times 10 to the 8th. Yeah, that's good. That's right. Everybody see that? because you're subtracting this, a minus minus. So it's 2 times 10 to the 8. Now, I'm going to stop this video right now, and then I'll start another video. So if this video doesn't work, at least I got the second video. All right? So here we go. Stop the video.